Hello everyone, welcome back to Machine Learning and I am your host Neeraj. In our previous sessions, we discussed about polynomial curve fitting and its implementation in Python. If you haven't watched those videos yet, you can find them on the channel page. From today onwards, we'll start our discussion of probability theory. Probability and linear algebra are the backbones of any machine learning algorithm. So we'll first cover these basics before diving into the most exciting machine learning algorithms. Today we'll cover why we need probability. We'll discuss about frequency interpretation of probability, what are joint, marginal and conditional probabilities, and finally we'll cover Bayes' theorem. Let's first start understanding why do we need probability. To do this, we can go back to our regression problem where we have access to only 10 noisy data points sampled from an underlying sine wave. The figure on your screen shows the available data points as blue bubbles and the underlying sine wave in green. Now when we try to estimate the underlying function from the available set of points, then there are two sources of uncertainty or randomness in the data. Noise is the first source of this uncertainty. You know that the points are not exactly on the true sine wave, but they deviate somewhat. But how much we do not know. So there is inherent uncertainty in the available data. The second source of uncertainty is the finite sample size. We have access to only 10 data points and you can combine these points in number of ways to generate some continuous signal. But how close that signal is to the original sine wave, that we do not know. And it's a question of model fitting. In such situations where we have some noise present in the data and we have access to only finite number of samples, probability gives us the tools to mathematically quantify these uncertainties and develop solutions for solving such pattern recognition problems. Let us now look at the formal frequency-based definition of probability. Suppose we have a red box containing 2 apples and 6 oranges. An act of picking a fruit from this box is known as an event or a trial or an experiment. This act is known as random trial when you pick a fruit without looking at it. Means you do not intentionally pick an apple or orange, but once picked it can be any one of these fruits. Now sample space is a set of possible outcomes a random experiment can take and it is denoted by omega. In our case, we have two elements in our sample space, an apple and an orange. We are now in good position to define a very important function known as random variable. Please note that random variable is neither random nor a variable. Rather, it is a function that maps the elements of a sample space to numerical values. Here, a random variable y assigns 1 to apple and 2 to orange. Finally, by frequency interpretation of probability, we can write the probability of picking an apple as equal to the ratio of number of apples to the total number of fruits in the box. That is py equals to 1 equals to 2 by 8. That is, there are 2 apples and 8 fruits in total, and this turns out to be 1 by 4. So probability of picking an apple is equals to 1 by 4 according to frequency interpretation of probability. Let's take this discussion further by looking at 2 boxes instead of 1. Our red box has 2 apples and 6 oranges, while the blue box has 3 apples and 1 orange. Now again we define our random experiment as an act of picking a fruit. But here is one additional level of complexity. When you go to pick a fruit, you have to first select a box from which you will make the pick. And selection of that box is itself random, and it is given that 40% of times you select red box and 60% of times the blue box is selected. This means that if you repeat the experiment of fruit selection 100 times, that is, you have 100 random trials, then out of those 100 trials, 40 times you will pick a fruit from the red box and 60 times from the blue box. This information is given to you and you convert this into probabilistic form by using random variable x to assign 1 and 2 to the selection of red and blue box respectively. Then the probability of selecting the red box can be written as p of x equals to 1 is equals to 40 by 100, which turns out to be 4 by 10. And similarly, the probability of selecting the blue box can be written as P of x equals to 2 is equals to 6 by 10. This understanding of random events and random variables allows us to introduce notations that will be used to develop further insights into probability theory. Let us denote the random variable for box selection by x. It can take one out of m values x1 to xm. In our fruit and box example, m is equals to 2, where x1 represents a red box and x2 represents blue box. Similarly, we denote the random variable for fruit selection as y, and it can take values from y1 to yl. L is also 2 in our example of fruit and box selection, where y1 represents apple and y2 represents orange. Now we can create a matrix as shown in this figure on your screen. Here choices of x are in the rows and y are in the columns. Suppose you have n trials, meaning that you select a fruit at random for n number of times. Then nij denotes the number of times out of n you selected ith box and jth fruit. For example, n12 represents the number of times an orange is selected from a red box. Let's further suppose that Ci indicates the number of times ith box is selected irrespective of the type of the fruit. Clearly, C1 is equal to the sum of the first row in this figure. That is, C1 is equals to N11 plus N12. Similarly, Rj is the number of times jth fruit is selected irrespective of the box type. Hence, R2 is equals to the sum of the second column in this figure, which is R2 equals to N12 plus N22. For simplicity, this can be written as summation over I of Ni2. With this notation in mind, we'll introduce very important concepts in probability theory, starting with joint and marginal probabilities. Joint probability is the probability of two or more random variables taking specific values in pairs. For example, we pick ith box and jth fruit. This means that our random variable x takes value xi and y takes on value yj. Formally, it is denoted as p of x equals to xi and y equals to yj and can be written as nij over n. For our fruit and box example, we can see from the adjoining figure that the probability of selecting a red box and an orange can be written as p of x equals to x1 and y equals to y2, which will be equal to n12 by n. Now, marginal probability is the probability of selecting a particular value of one random variable irrespective of another. For example, probability of selecting ith box can be written as p of x equals to xi, which will be simply the ratio of ci to n. Now, as you know, Ci is equals to the sum of the ith row in the adjoining figure. Thus, we can write Ci over n as summation over all possible values of j, that is, nij over n with summation over j. Now, look at the expression of joint probability, and we arrive at the sum rule of probability, which states that the marginal probability of a random variable x can be computed by summation over all possible values of random variable y from the joint probability of x and y. So this is known as the sum rule of probability. Now let us introduce the concept of conditional probabilities. A conditional probability indicates the probability of y equals to yj condition upon the knowledge that x is equals to xi. As per our previous diagram, the probability of y equals to yj given x equals to xj can be written as nij over ci. Let us elaborate this through our box and fruit example by asking, what is the probability of selecting an orange given you have selected a red box? In this case, we know that C1 is the number of times we will select a red box out of n trials, and out of C1 we select an orange n1 two times. Thus the conditional probability of y equals to y2 given x equals to x1 can be written as the ratio of n12 by C1. Now C1 can further be expanded as the summation of n11 plus n12. So this is the conditional probability. Now we know that the joint probability of x equals to xi and y equals to yj is equals to nij by n. If we divide and multiply this equation by ci and rearrange, then we get a very useful result which states that the joint probability is equal to the product of the conditional probability and the marginal of the random variable on which it is conditioned. That is, the probability of x equals to xi and y equals to yj can be written as the product of probability of y equals to yj given x equals to xi and probability of xi. This is known as the product rule of the probability.
The sum and product rule of probability can be used to derive Bayes' theorem, which is a central theme in pattern recognition and machine learning. Revisiting the sum rule, we can see that the marginal probability of x can be written as the sum over y of the joint probability of x and y. And by the product rule, the joint probability of x and y can be written as the product of the conditional probability of y given x and the marginal of x. Similarly, we can write the joint probability of y and x as equals to p of x given y multiplied by the marginal over y. Now by symmetry, p of y and x should be equal to p of x and y. So thus these two quantities on the right hand side of these equations can be equated. So when we equate these two quantities, we arrive at the Bayes theorem. So by Bayes theorem, we say that probability of y given x is equals to probability of x given y multiplied by py and divided by p of x. Now we can invoke the sum rule in the denominator to expand the marginal as p of x is equals to summation over y of the joint probability p, x and y. And in this denominator we can invoke the product rule to arrive at this equation. We will frequently revisit the Bayes theorem during our discussion of machine learning algorithms, but we'll stop now and look at some applications of the knowledge of probability gained so far. First question we want to answer is, what is the probability of selecting an apple? Formally, following our notation, we are asking what is p of y equals to y1. We know that the probability of selecting a red box and a blue box is equals to 4 by 10 and 6 by 10. That is, p of x equals to x1 equal to 4 by 10 and p of x equals to x2 is equals to 6 by 10. This given evidence is known as prior in probability theory. Now we can select an apple in two ways, by selecting a red box and then picking an apple from the red box, or we can select the blue box and pick an apple from the blue box. So using product and sum rule of probability, we can write p of y equals to y1 equals to p of y equal to y1 given x equals to x1, means we have selected an apple from red box and then we also multiply this quantity by the probability of selecting the red box, which is p x equals to x1, and we have to add this term with probability of selecting an apple from the blue box. By plugging in the values for these terms, we arrive at p y equals to y1 is equals to 11 by 20. So that is, selecting an apple irrespective of which box that comes from, the probability of selecting an apple is 11 by 20. Similarly, we can derive the probability of selecting an orange, which will be 9 by 20, and you can do the exercise yourself to verify these numbers. We can also ask questions like, what is the probability of selecting a red box given that we have picked up an orange? Formally, this boils down to asking what is the conditional probability of x equals to x1. Notice that x1 is our red box. given that y equals to y2. Again, we have access to the prior information about the relative chance of selecting a red or a blue box. We can invoke Bayes' theorem to answer such questions. So P of x equals to x1 given y equals to y2 can be written as P of y equal to y2 given x equals to x1 multiplied by px1 divided by P of y equals to y2. Now these quantities px1, P of y equals to y2, these are either known or previously computed. So we can just plug in those values here to come up with probability of x equals to x1 given y equals to y2 equals to 2 by 3. So you should do this exercise yourself and try to reproduce these results. Please note that P of x equals to xi is known as prior as it is given or known to us, and the conditional probability of x given y is called posterior because we have already observed a fruit and we want to know from which box it was picked. Thus posterior means post observation. Finally, the quantity P of y given x is known as likelihood in the sense that what is the likelihood or chance of selecting a particular fruit once we select a box. From Bayes' theorem, we can see that P of x given y is equals to P of y given x into P of x divided by P of y. Thus, from Bayes' theorem, it is evident that the posterior probability is proportional to the product of likelihood and prior. This is a very important result which we will revisit when we discuss maximum likelihood and maximum a posteriori estimate in coming sessions. In the next session, we will talk about probability density functions, expectation and covariance. Till then, stay tuned to machine learning and don't forget to like the video and subscribe to our YouTube channel. Thank you.